Hello, and welcome to Revolutionizing Your Information in 2020. Features you only get with RavenDB. Smartphones, tablets, portable servers like Raspberry Pi, and billions of edge devices are moving trillions upon trillions of data points per second. This poses enormous challenges for the database of 2020. As technology advances at breakneck speed, the mentality behind it stubbornly clings to the past. For forward-thinking solutions like RavenDB, you can enjoy abilities most databases don't offer, allowing you to accomplish feats with your application only a few can achieve. Today, RavenDB CEO Oren Eini gives you a guided tour of a set of features available only from the database that offers you in-memory performance along with persistence and asset integrity throughout your entire database. You will experience automatic indexing, lazy queries, transactional mergers, includes, automatic and aggressive caching in the box, and more. If you have any questions at any time, click the Q&A button at the bottom of your screen, and Oren will be happy to answer them at the end of the presentation. Enjoy, and here's Oren.
Hello, everyone. Thank you for joining me today. I love talking about RavenDB. I tend to focus on big-ticket items, how you can run it distributed fashion, failover and recovery, stuff that is amazing to see, amazing to look at. But the interesting here is that we've been building RavenDB for over a decade. And in that time frame, we have been writing tremendous amount of features. And a lot of them are there and incredibly useful, but you have to know about them. And this is what I want to talk about in today's webinar. Probably the most important thing that you have to know is the fallacies of distributed computing. And this is a very well-known topic, but people keep tripping on it. That's why they are fallacies, because there are things that people assume when they're writing distributed systems that are not true. And they tend to assume them because when you're developing a system, you're running on your local machine, and everything is fast, and there is no latency, and you can push as much data as you want, and you don't have to worry about someone sniffing the network. None of which is true for production systems. None of which is probably true even in your own network or inside the organization. So when we built RavenDB, I used to have a placard of these fallacies on the wall, just so I would remember them and know how to account for them. So let's talk about how you use RavenDB. RavenDB is we are always running the remote process. Even if you run in an embedded mode, we actually have a separate process. In small systems, maybe you're running as on the same machine, and typically you would run on a separate machine in the same data centers. If you run on the cloud, it may be very remote. So the question here, what are the implications of that? What does it mean if I'm always on the remote end? It means that it costs me quite a lot to make a query. So let's take a very simple scenario. I want to show just some orders data of a customer, which is about the simplest thing I could possibly think of. Now, let's go here. This is the live test. This is a silly little instance that we have that is publicly available. And you can see that here I have some companies, I have some orders, stuff like that. Not really that interesting or important. Let's go and look at some code. And you can see here that I'm connecting to not this instance, talking to the demo database. Now I want to show you some performance numbers. So the first thing I do nonsense operation just to force RavenDB to initiate a connection to the remote system, so we won't pay the TCP connection costs. And now here's my code. Open a new session, load the company, query of the recent orders by this company, and then I'm just saying, okay, let's go ahead and print that. I'm gathering all of the products from the recent orders. I'm printing out how much each order costs. I'm printing out whatever you want to order the recent products as well. And here you can see probably most important thing, how many queries I made to the database, how much time it took. Now, I'm running this from Israel. The live test instance is in either North Virginia or Oregon. I don't remember which. So there is a non-trivial latency between us. So I'm going to go here and run just this piece of code. And now we're going to wait. And that was not fun. Why do we get non-reference exception? I swear I tested this even a few minutes ago. Because someone was, what? This is really strange. Where do I have, oh. I think that someone decided to be fun with my database. So I'm going to switch to local instance. But obviously local instance isn't good, so let's try this way. If you're listening to this call, to this webinar, please don't mess with this publicly available database. Okay. Here we go. Now let's try to run it. And here we go. So you can see we're getting Alfred Futterkist. I probably killed the name. Here are some recent orders. Here are the item he ordered in the recent orders. Here are the information that we care about. So 11 requests to the server in 3.5 milliseconds. And here is a nice picture of a rhino because I like it. Let's run this again. And remember, this is, where is the code? This is the code that matters. But I see one query to the database, another query to the database. And at the same time, running the second time, he says that I'm querying at 11 requests. By the way, notice that we drop almost a whole second. This is probably because the intermediate appliances between my machine and the remote server are familiar with the route or something like that, but it's going to be stable about 2.5 to 2.7 seconds to run this. And the major problem is this guy, because it's so expensive. Let's try to analyze what's going on. So the first thing that we're going to do, we're going to monitor this guy. Or not, because apparently it doesn't work for something this big. So far we have had 0 requests in the session, which makes sense. Request number 1, request number 2, and let's just verify 2 requests to the database. Now we're going here, and now we're saying, oh, give me this product. And now I'm going to do something pretty bad. I just went again to the database. And you can see that I have a loop here. And this is a pretty common scenario. In fact, I intentionally wrote this in this way because this looks complex. I could have written it like this. Recent order, select many. Sorry. Oh, sorry. Okay. This might be easier to look at. So this and this effectively the same thing. And we can prove that by issuing the query again and seeing that we get 11 queries. And you can see exactly how slow it was. Like being very, very slow. Not good for us. And what happened, by the way, the difference between this and this is that this is innumerable. So we iterate that one at a time. Here we got everything in one shot. Now the problem is something like this is very easy to do by accident. And if you do something by accident, you can see that you have lots of query to the database. RavenDB has a very simple solution for this. We know when we make the query that we want to also get the orders. So let's see what we can do. Now, this is a very important line. It tells RavenDB when you query the order, I also want you to get to the lines product and getting the results. Let me see what this looks like. Now you can see something really amazing. Instead of going to the server 11 times, we only went twice. And the difference is between 2.6, 2.7 to 800. I want to understand this better. Now we can see something really interesting. Let's go and make the actual query. Now, here is the result. Here are 5 orders that I have. Now notice that I have here 2 tabs. One of them is for the result of the query. One of them is to get this. For each one of these orders, I'm going to the lines, getting the product, and fetching the related document. Because I told RavenDB that I would do that. So on the client side, once this is executed, calling this is in a rope, because I'm able to pull that directly from the session cache. So this include feature allows you to do quite a lot of optimizations without really having to think about that. Oh, I need to access related data? Sure, included, and then it's in memory, it's cheap. In fact, I could have, at this point, I'm only making 2 queries to the database. That's great. However, there is an issue here. I'm making 2 queries to the database. I don't like doing that. The reason I don't like doing that is that making a remote call costs me. In this case, it takes me about 800 milliseconds to render the first time. And I can do something much better. I can use something called lazy loading. So let's look at this. Instead of generating the query as before, I'm able to, let's see. Here's the first time. 2 queries on 1.3. Here's the second time, 1 request in 261 milliseconds. So the reduction in overall time to complete the system is amazing. And remember, I'm doing that on a system, on a server that is in a different continent than me, and a pretty poor one is at that. So here's the key. Instead of calling load, I'm calling lazy load. And instead of getting a query, I'm getting lazy of unknown. Now, here's what happens when I'm calling lazy. I'm not executing the query. Instead, what I'm doing, I'm registering the query in the session. And I'm saying, don't go to the database now. But when you do, make sure that you will give me this answer. So I can make as many queries like that as I want. And then I can either call this line or access the lazy property of one of them. In this case, I'm going to do a single remote call to the database. Let's see how this works from the point of view of the database. I'm running. Now I'm here. Not executed. Not executed. Perfect. Now, let's go to the database. And I'm going to look at the traffic watch. This tells me what's going on. And hours. Okay. Now, there's a lot of interesting details here, but this is what I care about. You can see here that I got a multi-get. And here are the internal of that. I make one remote call to the server, but I'm sending multiple requests. You can see here is the query, here is the load for the particular document, and everything works quite nicely for me. And I am able to reduce the cost by a lot. Remember, we started with a cost of 2.6 seconds. Now we are 10 times less. And this makes a lot of sense because we started with 11 queries to the database and we are not with 1. So this is almost a trick in many cases because it is so simple. It doesn't require really a lot of thinking, but it has huge impact on performance. Now, presumably you're not going to run with a database that is halfway across the world from you. You're going to run with someone a lot closer. But it means that you get a lot of benefits from reducing the costs. Because even if you move from, going to the database doesn't cost you 260 milliseconds, it costs you 1 millisecond. Then it's the cost of rendering the page in 1 millisecond or 50 milliseconds. And in many cases, if you multiply that by the number of concurrent accesses that we have, you're going to show quite a lot of interesting results. When you render a page today, you typically don't make just a single query to the database. You make a lot of them, and this can reduce the cost significantly. Now, interestingly enough, I made lots of queries here. In particular, I made this one. Notice this guy. I have an auto index here. Now, I've spoken about this before. This is one of the features that I really like, but I want to emphasize this. When you query RavenDB, the query goes to the index optimizer. The index optimizer is then able to decide, to the query optimizer. The query optimizer is then able to decide what is the best index, what is the best approach to execute this query. However, if there is no index that we can use, there is nothing we can do. At least in other databases, there's nothing, and you're forced to do a table or a collection scan, which is incredibly expensive. With RavenDB, we are going the other way around. We're going to say, if there is no index for that, the database is going to go ahead and create one for us, automatically on the fly. because that makes sense for us. That means that we are able to process queries efficiently and quickly. And creating an index in RavenDB doesn't mean that the entire system has gone to a hard, there are no lock-in or something, and nothing like that. Now, let's say that I want to add sales data for a customer. So let's see how I do that. There is actually an index that can give me that information. Here are the sales data for this customer. Now, I could actually go ahead and make a query. I can go here and add a query on this index. But even though it's the same query, I can actually do something more interesting and go the other way around. Notice what I'm doing here. I'm running a query on the company. So I'm running a query on this index by the company, and I'm also including the company that I'm querying on. Why am I doing that? Because in this case, I'm running the query in the include and the other query that I have, and then I get the value. And at this point, I'm done. I made one round trip to the server that included just 2 queries, because even though I have just one round trip, I still have to process however many queries I have. So by reducing that, I still get the benefit of this. So now I'm going to run the query, run this code, and here are the totals that I have. Everything happened in 2 requests to the database. That's interesting. It's not supposed to do that. Let's see why. Oh, because I'm sorry. Here's an interesting problem. Why do I have 2 queries here? I queried, I included. It should just work. But the key here, at this point, I haven't actually executed these queries. I have to explicitly do that or access the start.value to force the query. That's why I had 2 queries in here, and now I have 1 query, as expected. So the idea of there's a lot of cases where people ask me, I want to do a query in a query, do correlative subqueries, those sorts of things. RavenDB doesn't have this feature because it adds a lot of complexity both to the database implementation and to the performance profile of the database. In many cases, if you invert the way that you're thinking and use features such as include or lazy, you're able to get the same feature without having to deal with this level of complexity. Now, another issue that we have to deal with, again, fallacies of distributed computing, the notion of bandwidth, latency, and the number of calls that you're making. So here's an interesting observation. I'm going to run these 3 times. Let's see what we are actually getting from the database. So the first time, second time, and third time. So this is interesting because it means that the connection between the server is highly variable. I can't actually count on those numbers to tell me something. What I can do is this. Let's put a breakpoint here. You know what? It would be easier to show that. It's easier to show that without doing the lazy. Okay. Now, let's go to the traffic watch. And there we go. I want only on the demo. Here are my queries. Notice I got status 200. Now I'm making the query again. Now getting something a lot more interesting. Instead of getting status 200, I'm getting status 304. But what is this status 304? What does it mean? Well, it means something very simple. It means that when I'm making a query to RavenDB, the client remembers the query that I made and the answer that the server sent us. And whenever I make the same query again, we're going to tell the server, hey, I know what the answer to this question is. If you don't mind, only process this query if it changed. And if it changed, I'm going to get a new version here. Now, I'm going to get a new answer. Otherwise, I'm going to get 3 or 4. 3 or 4 is HTTP status unmodified, which means that, oh, just use whatever you have in your cache. Now, that means that I still have to go to the remote server. What I don't have to do, I don't have to pay the price of the server computing the query, and I don't have to pay the price of sending the data. And again, remember, queries may be very big, hundreds of kilobytes, multiple megabytes, stuff like that, and I just don't need to pay this price. Things become easier. Now, let's say that I'm going to go ahead and modify let's modify this guy. And now let's see how this works. We have a value cached in the database, but we got a new one because it was modified on the server side. So this is a feature that is always on with RavenDB. You don't have to do anything to make it work. The downside of this feature is that it's optimistic in nature. You have to go to the server to ask the question. And if the answer didn't change, you get a server bandwidth on some server-side processing, which is great. But remember that in this case, we are paying lots, just to be able to get the value from the server. Just to get the, oh, I haven't changed anything. So RavenDB also has another feature, this guy. And this is called aggressive caching. With aggressive caching, we're telling RavenDB something really interesting. Instead of going to the database, have the database talk to us. What do I mean by that? First of all, let's run this code and see how this works. For the scope of this method, all of the sessions here are going to be aggressively cached. And now we're going to see something really interesting. Here we have 2 requests at 400 milliseconds, 4 milliseconds, and 1 millisecond. This is ridiculous. And the only way that we can do that is by not going to the server at all. This is because here's what happened. When I say that aggressively cache behind the scenes, I'm going and opening a channel to the server. And I tell the server, hey, if anything changed, let me know. And then I remember the values that I have. And if I have the same query again, I serve it directly from the cache. Very, very fast. Very good. But I may miss out on updates. Let's see how this works. Okay, now, 1, 2. It's visible how long it takes. And here is the second time. Second time took 2 milliseconds. Now, I'm going to go here and modify the document again. Now, I'm going to run the query again. Let's see what it does. Oh, 1 second. I'm going to run this again because I'm pretty sure that when I marked here, it stopped it from printing or something like that. Okay. Let's do 3. Now let's retake this. And from the timing, you can see that we went to the database again. What happened was the RavenDB server said, oh, something was modified, and I got this client who wants to know about it. I will let him know about this. And the next query that they have from this client is going to need to go to the server again to know if something has changed or not. So for a lot of features, especially for the high-value targets, the main page, stuff like that, this can be an incredible boon for your performance because things just broke. And for the most part, even with aggressification, you're going to see mostly updated information. The reason that we require opt-in for aggressification is that it may violate some assumptions that we make. One of the consistent guarantees that we make in RavenDB is that any read after a write on the same node is going to see all previous writes. In this case, we're saying, oh, I want to violate that. I want to be able to prefer performance over consistency. Even though, because the server is going to talk to the client, even in this case, the consistency window is going to be relatively small. Now, you've probably had to write something like this. Probably many, many times. Some sort of a search engine over complex data. And the problem with doing something like this, especially if you have lots of data and, oh, I want to be able to filter by dates and date ranges and do basically be able to run, give the user the ability to run almost random queries, is that it's annoying, really, really, really annoying. What we can do instead is use RavenDB to do better. So let's see how this works. So we have the notion of a company, and this is what a company looks like. And we define an index in RavenDB. Now, indexes in RavenDB comes in several shapes. What you see here is the core definition of an index. And 1 second, we actually have an interesting question in here from Elton Nunes. I hope I'm answering that correctly. The question is, with aggressification is active in the server state, don't call me, I call you mode, and huge amount of data change. What's going on? So this is a really good answer. This is a really good question. I hope I will give a good answer. So with aggressification, what's actually happening is that whenever there is a change, the database is going to notify the client that something changed. It's not going to send you a notification for each and every change. The moment that anything changed on the server side, we just raise a flag. That's it. Now, this is done specifically to avoid the, 10,000 documents change, just send you 10,000 notification about changes. And from the client point of view, the moment that I get a change notification from the server, I treat my cache as non-authoritative, which means that I'm falling back to the usual caching behavior. I'm going to say, oh, I have this in the cache. Great. I'm going to go to the database, tell it what I have and what version I have, and then let it decide whatever it's going to give you new information, tell me all the information that I have is good. Once I get the confirmation from the server oh, this information is good, or here's some new information, I'm moving back to the aggressive caching mode for this particular piece of data. So we're not talking for each particular query, every particular request that you make to the server, it's going to be handled independently by RavenDB. It's have a different cache status. Going back to here, and so as I said, this is a way to define index by code. You can also define index in the studio and using JavaScript as you want. But let's talk about this index. This index basically says something like this. Okay, I have global index all of companies and create a single field called query that will have the name, external ID, and the contact name of the user. And we want to enable full text search on the query field. We want to enable suggestions on this field. So let's see what we are doing here. We're creating the index, blah, blah, blah. This is typically something that you do only at the beginning of your application or as part of administration deploy. We're getting some term from the user. We are doing a search. Let's do a real search. And we go ahead. Yes. Okay. While this is while I'm waiting for you to tell me what it's looking for, I'm running the search, and if I have results, I'm printing them. Just to make sure. Let's go here and see what the issue is. No, no issue. Here is the server-side representation of this index. And apparently it just doesn't want to come back. No, okay, not sure what happened here. I'm looking for alf key. And alf key, if you recall, is this guy. I can also look for, okay, that's good. Now, notice that here I have a typo, which means that we're not going to follow into this guy because there is no Alfredes. Instead, we're going to go here. Let's see what's going on. RavenDB is asking me, or this application is asking me, did you mean this? So it apparently fixed my typo. How did you do that? Let's go here. From index, company search. That's the right typo. And this is what I'm doing. I'm actually asking RavenDB, given the information that you have on this index, on this field, on which we enable suggestions, run string distance algorithm, do commutation, effectively do magic in order to figure out what the real value is. And Josh Model is telling me that my console window was in selection mode, output was passed in this case, which would exactly explain what's going on. So apparently I have lots of issues with the console mode today. So the idea here is that in very short amount of code, I'm able to produce features that looks like magic. Okay, and all sorts of stuff like that. Let's see some other good example that I can see. I'm looking Supremes. This is interesting. This is interesting because it uses the diatrics, I think that's the name. And that typically trips people up. And apparently there is something like this, which is the external ID for this guy. So it allows you to do a lot of fix-ups. It allows you to implement did you mean features, just like Google, with minimal amount of code, maximum amount of flexibility for the user. In fact, we can actually do better. It says, oh, if I have just one result here, I can just query this, pass it back here again, and figure out what the user meant. This is exactly how you would implement stuff at Google when you wrote something and you had a typo and they give you give you a query that says, oh, you probably meant this in this query, not this query. So we give you the right results for that. And I remember it can be freaky when you realize that what Google searched for is what you meant, not what you wrote. But when you actually understand how this works, it's really, it's not simple, but it's easy. It's easy to do that with almost no pain from your end. Now, I want to talk to you about a scenario. And the scenario is that I want to have some API. Every time that this API is called, I'm going to have, I want to charge a user 1 cent. So that's actually a real problem. How do I know how many calls a user made? And let's say that this is not, oh, let's go ahead and create any order. Let's say that I'm saying something like, oh, let's provide some information to the user or something like that. And I'm doing that over multiple concurrent calls, probably in distributed environments. So it's actually kind of hard to figure out how to do this properly. And let's think about how we're going to do that. So I'm going to have, this is the customer in question. And then I have a document per billing period. In this case, February of 2020, here is the bill for that. Now, great that I have a counter, I have a document per billing period, but how do I track access, concurrent and distributed accesses? The issue for that is that RavenDB has the notion of distributed counters. Let's see how this works. So the first thing that I want to do, I want to prepare for the API call. And this does something silly, such as create the appropriate document. Nothing really that interesting here. Let's go ahead and look at the document that we just created. This is what it done. Not really that interesting. Now, for each API call that I'm making, I'm doing the work that is required. This is not something that I care about. And then I'm going to say, okay, give me the right, this is the document ID that I need. And what I'm saying is, give me the right document for this billing period. And then I'm going to call this method. And this is a really interesting method because I'm saying, okay, let's increment a counter. And the counter isn't a value. It's for particular date and minute, an hour and minute that I'm running this. So let's see what this looks like. Let's run it again, again, and again. And running, and this doesn't actually do much in terms of user interface. But let's look what I have here. And now you can see this. So on the 21 day, we're using UTC. So this is 4 p.m. at 14 minutes. I made 3 queries. Now let's run it again. now we can start seeing what's going on. The idea here is that we use a document per billion period, and we use a counter per tracking period. So let's say that I want to show the user at some point how many queries they made per day, per hour, per minute, whatever. I'm using a counter per that period, and I'm just handling the rest. So all of the operations that happen in the same time period would be aggregated here. If I have concurrent usage, if I have two queries that happen at the same time, no worries, I'm going to get to the exact right value. Let's actually see that. Okay, and I think I need here like this. Right. Now, I'm going to run this 1,000 times concurrently. And let's see, you can see that we're getting updates. This is still being updated. We can probably go here and see what's going on. Notice that this is coming from my machine in Israel to this machine in somewhere around the US, North Virginia, Oregon, something like that. And here is the total. So highly concurrent writes, highly concurrent operations, and we get to the right value. So another issue here is that we also have what happens if we're running in a distributed environment. This is going to run just fine, and if you write it to multiple nodes at the same time, this is actually going to happen this is going to converge to the right value. Now, I have a question here from Robson, is whatever there is a documentation for that, and this is documented. The documentation is here. And there is quite a lot of stuff about this, and you can read all about the things that you can do about this, including doing things to these inquiries. I'm going to pass this in the chat. So Robson, now we have access for this. Now, this is lots of fun, but I want to also focus on another thing that happened here. I run this 1,000 times. If you recall, the description for this webinar said something about transaction merging. Let's go here. Let's look at the IO stats. RavenDB actually keep track of every single write that we do to the disk. And what I'm going to do now, I'm going to run this again. And let's see what we're actually doing. You can see here the writes to disk. You can see that we're writing 170 kilobytes. And so on here, actually quite a lot if you look at this. So the average size that we write here is about 172 kilobytes. But this is a really interesting number. Where did it come from? And the answer here is that because we are doing things in parallel, we're sending multiple requests to the server. One of the costliest things that RavenDB can do is write a disk, because this is so slow, like seriously slow. And because of that, RavenDB is not trying to write to the disk on every transaction. Instead, it's going to take all of the currently open transactions that we have pending and merge them all into a single request to the disk. remember that we talked about the fallacies of distributed computing? For the point of view of RavenDB, and this is really interesting, from the point of view of RavenDB, the disk is remote because it takes so long to get there. So we want to optimize that and only want to go to the database once. Sorry, only go to the disk once. You don't have to do anything about this, except remember that from the point of view of RavenDB, the absolute worst thing you can do is run things sequentially. Why is that? Because you have to wait to go to the server, and in the server, wait to go to this, come back to this, come back to your application, issue the next request. If at all possible, just stream data to RavenDB in parallel. It can handle that. It's going to be so much faster in the end. Now, another thing that I want to call attention to is this thing. Notice that I'm making multiple modifications at the same session. I'm making multiple modifications at the same sessions because I'm creating a new document and I'm updating or incrementing a counter on a totally different collection and document. All of this is transactional. If I fail to create the order, I'm also going to fail to increment the counter and vice versa. If you're doing things such as billing, this makes things a whole lot simpler because you don't really have to think about this. Oh, I'm just running things and everything works. So that's that. Now, the last, oh, no, 1 second. I forgot about this. Another feature that we have for counters is this. Yeah. Because of the... Okay. Now, notice this thing. What am I doing here? Here's my query. Oh, I have paid and not charged. Here's my query. Here is the total that I have here. And I'm querying this guy here. And I'm getting the right document. And I'm saying, OK, let's go to the metadata counters, get all of the counters that I have here, and sum them up. Give me the total result. Now I can use this to decide how much to charge the user. Probably after the end of the billing period, obviously, but that's the whole idea. And now, let's talk about time series. In order to talk about time series, I have to do a small change. This is running 4.2, but the time series are a new feature that is available only on the 5.0. Just so you understand, you can play with this now. Go to the nightly, and you can play with time series and how it works. There is also the client API for 5.0 is available on MyGet, not NuGet, MyGet. Okay, so now I'm going to go ahead and create this. Let's say that I'm trying to track some information about nodes in the system. And here I'm going to create some time series. That time series is going to represent a disk queue length over time for a bunch of disks. And go. Here's the disk queue. Now I'm going to look at this. And you can see here that I have the queue length here. And it moves, changes around. Notice something really interesting. I have a tag here. The tag tells me what device am I using. So all of this is in the same disk queue for the same value. it makes things easier to distinguish. But now that we have this, let's look what the API looks like. So we open the local thingy, and just like with counters, we say time series 4, we get node A, node 2A, and we run it. And now we're just going to say this. On current time, for this current drive, I'm going to say that the value that we're recording is 2.4, which is the disk queue length that I have. This is fun. This is fun because RavenDB is able to store this kind of data in a very efficient manner. We can compress this very nicely, and now we're able to run all sorts of interesting features around that. What do I mean? Let's look at this. So what I'm saying is very simple. On the nodes, I want 2 time series. One of them is for the OS disk queue, one of them is for the database disk queue. I can fit all the results. Group them on a 1-minute base and give me the max. I can go ahead and look at the details, max, stuff like that. Unfortunately, time series queries tend to result in a lot of data. And we currently have a bug in the studio that would cause it to crash when you're trying to display that much data in the preview. Luckily, we don't care about that because you can see that it's 3,000 results and lots of data. We can do things like this. And basically plot the data over time. Now, it's sort of hard to see the behavior here, but you can see it more clearly below. Where we peak and ebb, peak and ebb. You can also look, this is for the OS queue. Let's look at the database, and here we can see that over time, we are reaching higher and higher rates. Now, this is interesting. You can see that in this case, I have 300 results. That's nice. That's not a lot, but that's nice. Here is another case. Here I have 11 million items in heart rate. And I want to query, here we go. So what was my heart rate in this rate? And this is literally my data. I pulled this out of my Fitbit. Apparently here I did not wear the Fitbit. And that gives my average heart rate on a per week basis. And notice that, let me disable caching. So it takes me 64 milliseconds to process that amount of data. And you know what? Even so, no, let's look at this one. Now, here I have some data. And let's see if I remember how this works. Now, this is going to take a lot longer. The reason for that is that I have about 150 million records that I'm processing here. And notice that it took me less than a second and a half to process all of this. Now, I don't know how this is going to look like, but pretty much static all around, apparently. You have access to all of that through the client API, obviously, the ability to run queries and do all sorts of interesting stuff as you go along with this. I would really love you to go get the nightly builds and play with that. It's nightly quality, which means that it's pre-beta. We are still finding regular bugs all the time, but your feedback is really important, will be truly appreciated. And with that, it's time for questions. We already have one from Robson again. I think, yeah. So how difficult it is to change from SQL Server to RavenDB? And do you have experience with this? And what I will get with regards to performance? So we have migration, we have documentation about migration, and you can read all about this documentation. Okay, so you can, we have a wizard that will take your data from SQL into RavenDB, including do all of the appropriate transformations from the relational form to the document form. Migrating is an interesting experience because you also tend to build the system differently. If we go and look here at the orders, which is probably one of the most common, I create a lot of those. This is one of the common differences where I would have many tables to represent a single order, and with RavenDB, everything is in one shot. I think that we actually have a webinar planned in which I'm taking a relational application using a relational database, and I'm converting that into RavenDB. I think that we still haven't decided which application it's going to be, so if you have any suggestions, I would love to hear them. Any additional questions that you have? Stuff you would like to know? You don't have to think about it right now. If you want to, I will be very happy to answer any future questions. You can throw them into the mail list or send us an email, and we'll be very happy to answer. And with that, we are right on time to closing. I'm going to give everyone one last chance to ask a question. Okay. Thank you very much, guys.